In this sample problem, we're asked to do a bit of work with gravimetric stoichiometry. Problem reads, iron is the most widely used metal in North America. It may be produced by the reaction of iron 3 oxide, Fe2O3, with carbon monoxide to produce iron metal and carbon dioxide. What mass of iron 3 oxide is required to produce 100 grams of iron? So we're given a bit of information about the chemical reaction that's going on. The fact that it is the most widely used chemical or metal in North America is not relevant to answering the question, but it's part of the phrasing of the question. So it's not a distraction. It's not stuff that's just trying to make you read more. It is actually trying to phrase some of that as this is information that's relevant to why are we doing this calculation. What is really relevant, though, to actually solving the problem is that we're given the reaction here. So we're told that iron 3 oxide, Fe2O3, that will be solid, reacts with carbon monoxide, which is, of course, a gas, to produce pure iron metal and carbon dioxide. Now, quick look at this, not balanced in any way whatsoever. So very first thing we've got to do in order to solve this problem is we need to balance out this reaction. We need to make sure that the amount of chemicals on each side are the same. So I have iron, I have oxygen, and I have carbon. And I'm going to divide up my reaction into reactants and products. I have 2 irons in my reactant side. I have 3 plus 1 oxygens. And I have 1 carbon. Now, what I am actually going to do is I'm actually going to move the oxygen down to the bottom because since I have it in multiple chemicals, it's going to just be easier to deal with if it's on the bottom so I can write stuff underneath it. Doesn't really matter which order you put them in. I usually list stuff off in the order they appear on the reactant side, but in this case, I want the oxygen on the bottom so I can write below it. Make sure I don't run out of space. Then on the product side, I have 1 iron, I have 1 carbon, that should be a 2, not a 3. And I have 2 oxygens. Okay. I'm going to leave the iron until the end. And the reason that I'm going to leave this iron until the end is that iron on this side is on its own. That means it's going to be nice and easy to balance out. Carbon's also complicated, or oxygen's also complicated, but carbon's already balanced. So I can actually work on balancing out or trying to balance out my oxygens. Now, here's the challenge that you're going to get here. Multiply this by 2 to even it out, right? It gives us 4. But what happens when you add a 2 down here? You have to add a 2 up here. What does that do? That changes your carbons. Okay, I changed my carbons. I need to multiply my carbons here. Multiply it by 2. I have to put a 2 up front. It's going to change the carbons again, but it's also changing the oxygens here. Right? I'm not going to write it like that. I'm going to write it like this. So now I have 5 oxygens and I'm going in a circle. So that can be a bit of a challenge to deal with because we do need to balance out the carbons and the oxygens, and this is why I'm leaving the irons until the end. Because oftentimes there is a way that you can shortcut this. So we want to see how it is that we can get the carbon and the oxygen to balance out on both sides. Well, the easiest thing here is the carbon dioxide and the carbon monoxide have to be the same. So what I'm actually going to suggest doing is I'm going to suggest just upping the number of them by 1 and seeing if it balances out. Now, we've already done it with 2. We know 2 is going to send us in an endless loop. But let's try it with 3. Okay, if 3 doesn't work, I'm going to try it with 4. If 4 doesn't work, I'm going to try it with 5. And by that point, we could start fiddling around with the iron 3 oxide as well. But let's see about this. What if we multiply this by 3, this by 3, this by 3, and this by 3? Okay, cross this out. Gives us 3 plus 3 equals 6. Oh, hey! 2 times 3 gives us 6 as well. 1 times 3 gives us 3, and 1 times 3 gives us 3. So what I did there is I know that the carbon is only found in carbon monoxide and carbon dioxide. So I'm just going to progressively up the number. I tried it with 2 first, 2 doesn't work. Then I'm going to put them both up to 3 at the same time, and 3 happens to work out. So that works for us quite nicely. Then I just have to balance out my iron in the end, which is easy because I multiply it by 2. And the reason I left that until the end is I didn't know if I had to change the iron 3 oxide. Because I didn't know if I had to change it, this is nice and easy, nice and simple to balance right here, because it's just iron on its own. So I just left it till the end to make sure that nothing was going to mess that up. I could just balance that once, unlike the stuff I had to do with carbon and oxygen. Okay, I'm erasing. You might want to rewrite this if you're writing on paper. But now I have a balanced chemical equation. So I've got to do my stoichiometry from here. So what I'm going to do is I'm going to start writing out my knowns and unknown. I know that I want to have 100 grams of iron in the end. And important thing with this as well, you don't necessarily have to write it in the knowns and unknowns, but in stoichiometry, you have to include the chemical that's part of the grams. I want to know how much iron 3 oxide. That's going to be an unknown number of grams of Fe2O3. Then I'm going to need some molar mass. So that means I need to go to the periodic table. Looking at the periodic table for iron, I see the molar mass of the iron is going to be equal to 55 and 85 hundredths of a gram per mole. Make your grams look a bit less like an 8 maybe. For the iron 3 oxide, I'm not told it directly, but I can figure it out. I need 2 copies of the 55 and 85 hundredths. And I need 3 copies of oxygen's molar mass of 16. Okay. I'm just going to plug that into my calculator. That gives me 159 and 7/10 of a gram per mole. Okay. Last thing that I need here is I need a ratio. Now I see here, I'm going to be starting with iron on this side. So I'm going to want iron to be on the bottom of the ratio. I have, for every 2 moles of iron, I have 1 mole of iron 3 oxide. Or I could say I have 1 mole of iron 3 oxide for every 2 moles of iron. I'm putting the iron on the bottom because I know I'm going to want to cancel that out because that's the chemical I'm starting with. I want to end with the iron 3 oxide. Then I often like to include an arrow when I do this. And all that the arrow is doing is it's helping me frame the direction that I'm going to be moving with my numbers as I write them out. I'm going to start out with my stuff over here, then I'm going to do my molar mass, then I'm going to do my ratio, then I'm going to use my other molar mass, and that's going to end me with grams. There's nothing that's actually part of stoichiometry. I just find that this is a useful trick that helps people structure the way they write out the question if they have a bit of difficulty with unit canceling or remembering what goes in what order. Also, as well, all the stuff we're doing is multiplication, so the order doesn't necessarily matter, but we do want to maintain some structure to this question conceptually. And that's really important because we have multiple values that have the same units in them. So it's really easy to say, get your molar masses mixed up. So by maintaining a bit of structure and order as we write this out, it will actually make our lives a little bit easier. So we're looking for a mass in the end. We are going to start with our 100 grams of iron. Note that I am including the iron in that. I have to actually write that out. Next, I'm going to write out iron's molar mass. Now, I want to cancel out the grams because when I put in the ratio, it has to be a ratio of moles. So I'm going to put the grams on the bottom to unit cancel them out. This is where unit analysis becomes really important. And I'm using this molar mass because it's the molar mass of this chemical. I have to always make sure the molar mass is being used for the appropriate chemical when I do my stoichiometry. Next up, I'm going to include the ratio, and this is where I unit cancel out the iron and switch it over to the iron 3 oxide. Okay, and then the very last thing we need in this is we need to go from moles back to mass. So we are going to need that second molar mass for the iron 3 oxide. And that's the equation that I need in order to figure this out. It's going to convert the 100 grams of iron into the mass of the iron 3 oxide. And important thing to remember with this as well is that these aren't equal values, but they're equivalent to each other. So as we're doing this calculation, the equal sign means something a little bit different than how we usually refer to it in mathematics. The equal sign in stoichiometry doesn't mean that, oh, these are equal comparable things. They're not. Two chemicals are not equal to each other in chemistry. But what it does mean is that the number we get in the end is going to be equivalent of the amount of 100 grams of iron. So we're calculating what is the equivalent amount of iron 3 oxide. And that gives us a number. If I plug everything in correctly, which I have not done, that gives us a number of 143 grams. And when I write this out, I'm including the chemical. The question is wrong if you don't include the chemical. Not because the math is wrong, but because you have to be specific here. What chemical were you calculating for? And that might seem like, oh, but why do I have to be specific? But here's the thing. If I look at this and I see that you've got the wrong number as your final answer, but you've told me which chemical it is, and I see that you accidentally picked the wrong chemical to do your calculations, it makes it easier for me to give you part marks on that. So I can still see, oh, you didn't answer what I asked you to answer on that question, but I can still see that you're doing the correct processes. You're not correct with your answer. You need to work on reading the question carefully, but I can give you some marks for showing that you do understand the processes that I'm trying to assess.